There is increased interest in using generative AI to create 3D spaces for VR applications. However, today's models overlook core VR usability requirements and produce artificial environments, falling short of supporting VR collaborative tasks that benefit from incorporating the user's physical context. To generate environments that support VR telepresence, we introduced SpaceBlender, a pipeline utilizing generative AI techniques to transform user-provided 2D images into context-rich 3D environments. We build on the existing text-to-room pipeline, which enables the generation of textured 3D meshes of indoor scenes from text prompts or single input images through an iterative mesh generation process. This is guided by predefined camera trajectories and text prompts. While this pipeline's implementation is flexible due to its usage of models in the 2D image domain, its assumptions and limitations form technical barriers to generating unified environments from disparate input images suitable for VR telepresence applications. We defined 4 requirements to address this. In summary, we aim to integrate spatial inputs from various perspectives through semantic floorplane alignment, enable coherent scene blending for context-rich environments via geometric prior meshes and multi-diffusion-based image completion, simplify user experience using automatically generated trajectory sequences and dynamic prompt generation, and support VR usability with consistent geometric room structures for comfortable navigation. The SpaceBlender pipeline consists of 2 stages. The first runs once per generation, and the second involves an iterative process. The first stage starts with an image pre-processing step to remove any humans detected by the one-former semantic segmentation model, after which depth estimation and back projection are used to create 3D submeshes from the input images. Following this, the submeshes are aligned to a common floor plane through a ransack-based method, which fits a plane to vertices matching with projected semantic floor labels. If no floor is present in an input image, we generate a floor through a downward mesh generation trajectory, using a prompt defined by a large language model that is passed an inferred image caption of the input image. After alignment, submeshes are arranged with a parameter-based layout technique that positions them on the perimeter of a circle. The diameter of this circle is determined through parameter d, defining the size of the blended space between the submeshes. The geometric prior is then defined as the convex hull of this layout. To generate text prompts for the iterative blending process, we utilize a large language model instructed to act as an interior architect. Given a set of inferred descriptions of each submesh, this model is tasked to produce creative descriptions of the connecting spaces. Entering the second stage of the pipeline, for each step, a view of the current state of the mesh is rendered, resulting in an RGB image and a mask indicating missing regions of the mesh. Along with this, SpaceBlender renders a view of the geometric prior mesh. From the same viewpoint, a depth map of this mesh is rendered and used as a depth prior image. A layout prior image is calculated based on the depth gradients to define an outline of the space. These priors are then used for the image completion step using the pre-trained ControlNet depth model, as well as a custom-trained ControlNet layout model that guides the shape of the space without limiting generation of furniture. The RGB mask and prior images are then passed to an image and painting model, combined with multi-diffusion to enable completion of wide images. The output is processed with the semantic segmentation model, and any depth values overlapping with the semantic labels of the floor, wall, or ceiling are overlaid with the rendered depth of the scene and passed to the iron depth in painting model. The output is then back projected into world space. This process continues until all empty regions between submeshes are filled. To fill the remaining gaps, we define custom mesh completion trajectories. These include trajectories pointing upwards and downwards, as well as trajectories that interpolate from the center point of the blended space to each submesh. Lastly, we naively simulate a user looking around to fill in gaps that could be noticeable from typical user perspectives. In a preliminary within-subject study where 20 participants performed a VR-based affinity diagramming task in pairs, we compared SpaceBlender with a generic environment and text-to-room, evaluating its ability to create virtual spaces suitable for VR collaboration. Overall, participants experienced increased physical comfort and navigability in the generic and SpaceBlender conditions due to greater geometric consistency, and some leveraged recognizable or familiar environmental features in the SpaceBlender space to complete the task. We refer to our paper for further details on our pipeline and study.